Welcome to today's lecture on mechanical energy balances. In the previous lecture, we looked at some of the introduction aspects of energy balances. We primarily focused on chemical processes. Today, we will talk about mechanical processes which are seen in any chemical and biochemical industry. What is the difference between a chemical and a mechanical process? A chemical process would be something like a reactor or a distillation column, evaporators, heat exchangers, etc. In such systems, shaft work, kinetic energy and potential energy changes are not very critical. However, you would have heat and change in internal energy or enthalpy which play a major role when it comes to energy balance calculations. In one of the earlier problems, we tried to identify the change in kinetic energy and also incorporate that while we performed energy balance calculations. But if you remember, we saw that the effect of change in kinetic energy was very small and it was about 1/100th of the effect of change in enthalpy. So, such processes where change in enthalpy and heat or change in internal energy and heat play a major role are called as the chemical processes. So, you would use internal energy for closed systems and enthalpy changes for open systems. There are another type of process which is called as the mechanical process. Processes like compression of gases or pumping of liquids are mechanical processes. Here shaft work, change in kinetic and potential energies are much more crucial. Heat flow and internal energy changes are secondary. This is because here usually there is not a big change in temperature. There might be some change in temperature, but that is not very significant. So, for this reason, for these processes which are called as the mechanical processes, we are more concerned about accounting for shaft work and change in kinetic and potential energies. Let us look at some of these systems and let us try to derive how an energy balance equation would look like for such mechanical processes. What you see here is a mechanical process. There is a collection tank which basically collects the bio waste from the drain, and this bio waste is then pumped using a feed pump to the treatment plant. You need to perform mechanical energy balances to calculate what size pump should be used, what should be the capacity of the pump, and what would be the pressure drop which occurs between the collection tank drain and the pipeline to the treatment plant. So, to understand and know these values is crucial for designing appropriate equipment. For this reason, we need to fully understand how to perform mechanical energy balances. What is a mechanical energy balance equation? We already had energy balance equations for open and closed systems. Those were general energy balance equations. Now, let us convert them to mechanical energy balances where focus is primarily on shaft work, kinetic energy and potential energy changes. For an open system at steady state, energy balance equation becomes input equals output. From the general energy balance equation for an open system, we have delta H dot plus delta Ek dot plus delta Ep dot equals Q dot minus Ws dot. This delta H dot can be written in terms of internal energy and specific volume. So, let us do that. The delta H dot value you have can actually be written in terms of internal energy. So, then the equation would become delta U dot plus delta of PV dot plus Ek dot, which would be m dot delta U squared divided by 2 plus Ep dot, which would be m dot G delta Z equals Q dot minus Ws dot. This entire equation can be divided by m dot. So, when we do this, what you end up with is delta U cap plus delta PV cap plus delta U squared by 2 plus G delta Z equals Q dot minus Ws dot divided by m dot. Rearranging this equation, we can get delta P divided by rho plus delta U square by 2 plus G delta Z plus delta U cap minus Q dot divided by m dot would be equal to minus Ws dot divided by m dot. What I have done here is delta P times V cap I have converted to delta P divided by rho. V cap is specific volume which is equal to 1 by rho. So, by substituting density in terms of specific volume, we get delta P divided by rho instead of delta P V cap. So, the rest of the terms are the same except for some rearrangements in the equation. The term within the bracket, which is delta U cap minus Q dot divided by M dot, is also called as friction factor, which can be written as F prime. So, the equation then becomes delta P divided by rho plus delta U square by 2 plus G delta Z plus F cap equals minus Ws dot divided by M dot. In situations where friction factor is equal to 0, such as smooth pipes and things like that, this F prime or F cap can actually be equated to 0. So, friction factor can be 0 in certain conditions. If shaft work is also 0, then Ws dot will also be equal to 0, giving the equation delta P divided by rho plus delta U square by 2 plus G delta Z equals 0. The first equation we have here, which is delta P divided by rho plus delta U squared plus G delta Z plus F cap equals minus Ws dot divided by M dot, is called as the general mechanical energy balance equation. The second equation which I have at the end, which is delta P divided by rho plus delta U squared by 2 plus G delta Z equals 0, is the Bernoulli's equation. It is a simplified form of mechanical energy balance equation applicable to specific systems where there is no friction or shaft work. So, with this derivation we can move on to performing some mechanical energy balance problems. Here is the first example problem. Water flows through the system shown here at a rate of 20 liters per minute. Estimate the pressure required at point 1 if friction loss is negligible. So, you have been given a system where water is flowing, you have also been told that friction loss is negligible. So, using the system, let us perform mechanical energy balance calculations. The general mechanical energy balance equation would be delta P divided by rho plus delta U squared by 2 plus G delta Z plus F cap equals minus Ws dot divided by M dot. In this system, we have been told that there is no friction, which means the friction factor can be equated to 0, and we also know that there is no shaft work because there are no moving parts in the system, which means Ws also goes to 0. So, for this system we can use the Bernoulli's equation for performing mechanical energy balances. So, the Bernoulli's equation is delta P divided by rho plus delta U squared by 2 plus G delta Z equals 0. We have been asked to calculate the pressure at point 1. We also have the information about pressure at point 2, which is 1 atmosphere. We have information about delta Z because we know the difference in the height between point 1 and point 2 is 50 meters. The value we need to calculate is delta U squared. For this we need to know the velocity of water flowing at point 1 and point 2. As the cross sectional areas are different, the velocities would also be different. Based on the volumetric flow rate, which is 20 liters per minute, we can calculate the velocity or the linear velocity as volumetric flow rate divided by cross sectional area. So, let us try and do that. Linear velocity at point 1 u1 would be equal to 20 liters per minute, and if you want to convert this liters to meter, it would be meter cube, it would be 1 meter cube contains 1000 liters times, we also have to convert minutes to seconds, which would be 1 minute contains 60 seconds. So, this is now converted to meter cube per second. We want to divide this by cross sectional area, which would be pi r squared. Pi is 3.14, r here is 0.25 squared. This 0.25 is the radius of the pipe at point 1. So, this is in terms of centimeters. So, we need to convert this to meters. So, this is actually centimeter squared. So, we want to convert this to meter squared. So, this would be 1 meter squared contains 10 power 4 centimeter squared. So, in this equation you have centimeter squared getting cancelled, minute getting cancelled, liters getting cancelled, meter squares getting cancelled, and you end up with meters per second, which is the linear velocity. So, u1 is actually equal to 17 meters per second. Similarly, you can calculate u2, which would be equal to 4.24 meters per second. You actually do not have to perform all the calculations which we did to calculate u2. What you see is the cross sectional area at point 2 is going to be 4 times the cross sectional area at point 1. This is because you have the radius which is twice the radius of point 1 at point 2. So, the radius at point 2 is 2 times the radius at point 1, which means the cross sectional area at point 2 will be 4 times the cross sectional area at point 1. This means the linear velocity will be 1/4 of the linear velocity at point 1. So, therefore, we get u2 equals 4.24 meters per second. So, we need to calculate delta u squared, which would be u2 squared minus u1 squared, which is 4.24 squared minus 17 squared, giving a change in velocity squared as minus 271 meter squared per second squared. We can substitute this value to the Bernoulli's equation and we will be able to calculate the pressure drop. We have delta P which is equal to P2 minus P1, and we have delta Z equal to 50 meters, and we have delta U squared equal to minus 271 meter squared per second squared. So, here we already know the value for P1, which is 1 atmosphere, that is equivalent to 1.013 times 10 power 5 pascals. Now, using this value we can substitute all of them into the Bernoulli's equation, which is delta P divided by rho plus delta U squared by 2 plus G delta Z equals 0. Substituting all these values, we can get the value for pressure at point 1 as 4.56 bar. Please perform appropriate unit conversions to verify if the value I have is correct. Moving on to the next problem, we will try and solve this example problem where all the parameters are given to us in American engineering units. If you are not familiar with American engineering units, I recommend that you rewatch the video where we discussed units and dimensions. I would have gone through the aspects related to American engineering system. We will try and apply those principles here in this problem, and you will be able to understand what are unique to American engineering system. Gasoline with density of 50 pound mass per feet cube is to be siphoned from a tank. The friction loss in the line is 0.8 feet pound force per pound mass. Estimate how long it will take to siphon 5 gallons, neglecting the change in liquid level in the gasoline tank during the process and assuming that point 1 and point 2 are at 1 atmosphere. So, here you have a friction loss. The friction loss term uses pound force. As I mentioned right now, you should go back and look up the video on units and dimensions to understand the inherent problems with pound force term. You should try to remember and recollect what GC, which is the conversion factor, represents. We will apply that conversion factor while we are solving this problem. The general mechanical energy balance would be delta P divided by rho plus delta U squared by 2 plus G delta Z plus F cap equals minus Ws dot divided by m dot. So, here we have been told that the pressure at point 1 and point 2 are both 1 atmosphere, which means delta P would be equal to 0. We also do not have any moving parts in this system, which means shaft work will be equal to 0. We do have a change in height, there is a 2.5 feet change in height, and we also would have a change in velocity, because at point 1 water is stationary inside the tank, and at point 2 you actually have water flowing out of the pipe. So, there would be some velocity at point 2. So, there is going to be a delta u squared, f cap has also been given. Now, let us try to calculate each of these parameters. Delta u squared would be equal to u2 squared, because u1 squared is 0, and delta z is equal to minus 2.5 feet, and you have also been given f cap is equal to 0.8 pound force times feet divided by pound mass. Now, let us look at each of the terms and try to understand what units they would be in. We ultimately have to have all the units in terms of feet pound force per pound mass for the equation to be valid. That is the rule for dimensional homogeneity. So, taking that into account, the u2 squared divided by 2 which you would calculate would actually be in terms of feet squared per second squared. This now needs to be converted to feet times pound force divided by pound mass. The second term which you would calculate is in terms of delta z times g. So, g is acceleration due to gravity, which would be feet per second squared, and delta z would again be feet. So, therefore, the units for delta z times g would also be feet squared by second squared. This also needs to be converted to pound force times feet divided by pound mass. If you remember the term conversion factor Gc, we know that Gc is numerically equal to the acceleration due to gravity at 45° latitude. So, this would be 32.174. If you remember the units, that the units for Gc would be pound mass times feet divided by pound force times second squared. By using this Gc appropriately in each of these terms, we can convert all these terms to the same units. So, what you would have is u2 squared divided by 2 times feet squared per second squared divided by Gc, which would give you units of pound force divided by pound mass times feet second squared. So, this would be the units for Gc. So, here you would have the second squared cancelled, feet cancelled, and you would be having the final units as feet times pound force divided by pound mass, which is the same units as the friction factor which has been given, plus you have 32.174 which is the g value in the g delta z. The units for this would be feet per second squared times delta z, which is minus 2.5 feet, and this again divided by Gc, the units being pound force second squared divided by pound mass feet. So, you would have feet and second squared cancelled, and you would have the same units as f cap, plus f cap is equal to 0. So, what happens here is you would have to calculate u2 squared and you would be able to solve this problem, because we already know the value for Gc is 32.174 pound mass feet per pound force second squared. Substituting the value for Gc into this equation and also accounting for f cap, we will be able to calculate the value for u2, which is the velocity at point 2. u2 would be equal to 10.5 feet per second. So, this is the linear velocity. We have been asked to calculate the time taken for siphoning 5 gallons, which means we need to know the volumetric flow rate. So, we can convert this linear velocity to volumetric flow rate by multiplying it with the cross sectional area. The cross sectional area for the pipe can be calculated using the inner diameter of the pipe. Volumetric flow rate would be equal to velocity, which is 10.5 in terms of feet per second, times cross sectional area, which is 3.14 or pi, times r squared, r is 0.125 inch squared, and this inch can be converted to feet as 1 feet is basically 12 inches, and using this we would get volumetric flow rate as 3.58 times 10 power minus 3 feet cube per second. This gives us the volumetric flow rate in terms of feet cube per second. We now need to calculate the time taken for draining 5 gallons of gasoline. So, time taken would be equal to volume divided by volumetric flow rate. Volumetric flow rate. However, here volume is given in terms of gallons and flow rate is in terms of feet cube per second. We need to know the conversion factor for 1 gallon to feet cube. So, 1 gallon is equal to 0.1337 feet cube. So, using that we know 5 gallons would be 0.1337 times 5 divided by 3.58 times 10 power minus 3, which is the volumetric flow rate, giving the total time taken as 187 seconds. So, it takes approximately 187 seconds to drain 5 gallons of gasoline from this system. With this you would have seen how American engineering system is used, how the conversion factor GC has to be applied while we perform calculations involving the term pound force. We also looked at a conversion factor from gallon to volumetric flow rate in terms of feet cube. So, converting gallon to feet cube, we had to use a conversion factor which was not an easy number to remember, unlike what we usually use in SI units. With this we have come to the conclusion of mechanical energy balances. We will perform some tutorial problems in the next lecture. Until then, thank you and goodbye.